The term cryptography is actually originated from, a Greek word, and in Greek, crypt means secret and graph means writing. Okay, so actually, in the olden times, like in 20th century, cryptography is largely related with language pattern, how you are writing it, somehow secretly you are writing some message. And from there, this cryptography, came from, right? So its origin is from Greece. Now, so this is, I'm telling you about 20th century, but currently, cryptography refers to the study of mathematical techniques. And why mathematical, I'm saying? Because now it is no, not more dependent upon the language and its pattern, but it is more towards the mathematical techniques that are derived, in due course of time, which actually help us in providing our goals, our security related goals that we have covered till now. Okay. Some of the goals are confidentiality, integrity, authentication, availability, non-repudiation, privacy, anonymity, etc. So to achieve these security related goals, we have properly formulated mathematical techniques. Okay, we can mathematically prove that how this particular algorithm will help us to achieve the goal, say confidentiality or something like that, right? So therefore, now cryptography actually refers to the study of mathematical techniques to achieve various security related goals. Okay. So the word does not refer to means of providing information security, but rather it is a subset of techniques. It is somehow, you can call it as a toolkit, right? Toolkit which contain many tools and techniques which help us to achieve our security goals. Okay, so in this particular chain of lectures, we will going to explore some of these techniques and learn more about the strengths and weaknesses of different security mechanisms which are there, right? Okay. So if you can recall from our last lecture that was on design principles, so we have explored a lot about principle of open design, principle of minimizing secrets, etc. So in this particular, series of lecture, we will focus more on these two principles, right? If you remember, when I am quoting some examples related to open design and minimizing secrets, again and again I keep on going examples. I am taking examples from cryptographic system, right? The reason is, you will actually see the beauty of these principles or the need of these principles when you learn more about crypto systems, right? So with this respect, let me define two different types of design. One is a closed design, which is generally used in military communication or embassy communication, which was held, during the world wars. So at that time, what they decided is they decided to keep the actual algorithm as secret, right? And therefore, it is called a closed design. So they come up with an algorithm, okay, an algorithm which can somehow, uh, jumble the message which is written, or somehow do something to the message so that it is not remain in the readable or meaningful format, right? This technique is also known as encryption, by the way. So they actually come up with many encryption algorithms, but the security of these algorithms lies in the secrecy of, designing of the algorithm. Okay, so they have to keep the actual algorithm secret. Nobody knows how you have encrypted this data, how you have jumbled this data to produce, this secret code or something like that, right? Now, the problem with this system is if the detail of the algorithm leaked, and it will actually going to leak over a period of time, right? As soon as the algorithm leak, it becomes insecure because now everything is out. Okay. I mean, everybody knows what actually you are doing. inside the algorithm. Okay. But over a period of time, we also realize that secrecy is not same as security. If something is secret, it is secure, you cannot say that, right? And it is very possible, or it is very probable that, details about the algorithm will be leaked over a period of time. Because somehow, if you are keeping the algorithm secret, we are actually, propagating the proprietary of the design, right? And whenever there is a proprietary on a particular design, then you are relying all your security on that particular company or the organization who has developed that particular algorithm. Okay. And in that sense, if people cannot see it, it cannot be audited, as we have discussed. So we have to make the design open so that everybody can audit it, everybody can see it, and everybody can validate that yes, this is a secure algorithm. Otherwise, what happened? One company who developed the algorithm XYZ, they will claim that my algorithm is the safest algorithm. Okay, but who will going to audit this until unless some attack has happened? Okay, so that is the problem with closed design. And we have already discussed that, principle of open design in that sense is quite a useful principle to have in our system. Okay, so the principle of open design is actually also known as Kirchhoff's principle or Kirchhoff's law. Okay. So Kirchhoff is actually a cryptographer, a very good cryptographer, a very famous cryptographer rather of 19th century. So what he said is a crypto system should be secure even if everything about the system except the key, right? So we are now coming to the principle of minimizing the secret, except the key is in public knowledge. Okay, this is what Kirchhoff's principle is. So it is nothing but the open design principle, right? That he said that you can consider a crypto system to be secure if everything of the system is out except a minimum possible information that could be in the form of key or something like that. But still, nobody is able to decrypt the data that is encrypted by that algorithm. The algorithm is available for the public to see it. Everybody knows what procedure we are following to encrypt this particular data, but still nobody is able to decrypt the data until he or she does not possess the secret, minimum secret information which was there. Okay, so the algorithm actually relies on the secret input, also known as a key, that is required for encryption as well as for proper decryption, right? So definitely whatever we have learned from now onwards, we will always, promote open design, and whatever algorithm we will see, we will actually see the algorithm which actually follow principle of open design, right? So definitely, because this is considered a good practice, because it allows many individual and organization to audit the code, to audit the algorithm, and to report back the issues which they may find in that algorithm. Okay, so it is well checked, well audited algorithm, and therefore considered as more secure. Let me formally define what a crypto system means, right? So a crypto system is a quintuple. Okay, so quintuple means a tuple with having 5 elements in it. Now these 5 elements are such that out of these 3 elements, that is M, K, and C, are finite sets. M represents set of plain text. Okay, the plain text that we want to send somewhere. So for example, let's take an example, hello. So hello is a plain text which any human, it is human readable, human understandable, and human know what does this mean, what does hello means. Okay, so they can derive some meaningful information out of this particular message, and this is considered as plain text message. There is another set called K. K is a set of keys. So again and again, we are focusing on, minimizing the secret principle. So the minimum possible secret which is there, which is, actually the key feature of a secure algorithm. So K, capital K, is a set of all such keys which can be used in the process, right? What is C? C is a set of ciphertext. Now, what do you mean by ciphertext? Suppose somehow I encrypt this message, I jumbled this message, or I did something with this particular message, and I have created another message XYZPB. Okay, so now this is this is called a ciphertext. Now there is another element E. E is a set of encryption functions. Okay, encryption function such that the function looks like M cross K. Okay, will give you C. So M, any message from the set M, if combined with, or there is some function which we put along with, say, small k or k1, this is a key, it will give us the output, or this function will take us to something which may be C1, which belongs to capital C. Okay, so capital C is a set of ciphertext, and this is a ordered relationship. So if we take a message, we perform some function by taking K1 key into consideration, it will give us a ciphertext known as C1, and this ciphertext actually belongs to capital C, where capital C is a set of all possible ciphertext. Okay. Similarly, decryption is another function which will perform operation on C, and it will take another key, say K2, into consideration. K2 again belongs to capital key. Okay, and it will give us the plain text. Okay, whatever message it will give us, it belongs to our plain text format. Okay, so E and D are set of encryption and decryption functions respectively, whereas M, K, and C are finite sets belonging to plain text, key, and ciphertext respectively. Now, for each key E, which belongs to K, so now E belongs to K, there exists another key D, let's say D, which again belongs to K. K is a set of keys, if you remember, such that for each P belongs to P. Now, this is actually M belongs to capital M, similar to that. Okay, so I am using P and M interchangeably. P means plain text, again set of plain text, and M also means set of plain text. Okay, so for each key E which belongs to K, there should exist, or there exists another key D which belongs to K, such that if we encrypt any message using key E, okay, when on the output of that encrypted data, or on that ciphertext, if we apply decryption mechanism using key D, it will again give us the plain text, right? So for example, I am converting hello to some ciphertext, and suppose I am using small e key here. Okay, and I am actually doing this with some encryption algorithm E, right? So now what happened, when I apply encryption algorithm E on hello, the output is this. Okay, so if on the output, so I am applying encryption on hello, the output is XYZPB. Now on this particular output, if I apply decryption mechanism, okay, or a decryption algorithm, so on XYZPB, if I apply decryption using key D, okay, then it will give me again the plain text, right? So XYZPB is nothing but it is the encryption of hello. This is what written here. Okay, so if you yes, please.
Ma'am, here D and E should be same.
D and E.
Yes, ma'am. The key D and the ED.
Yes,
key.
we will. Yes, we will come to that part in a minute. Okay, we will come to that part. It could be same, it could be different. So we will come to this thing. Okay. Yeah. So can you see this formula, right? So whenever you apply encryption on a plain text message, and then on the output, if you apply decryption, again you are able to get the plain text, right? And this is what we want. So if suppose I would like to send an encrypted message to you, what I will do, I will take that message, plain text message, the actual message, the readable message, I will encrypt it, send it to you. Now you can actually able to decrypt it and get back again the plain text, right? Anybody in between, if can get the access of this encrypted text, also known as ciphertext, they cannot actually derive any meaningful information out of it. Okay, and this is how the idea is, you can achieve confidentiality. Two types of crypto system. Okay, the first crypto system is known as symmetric crypto system, or private key crypto system, or secret key crypto system. Okay, so there are many names, or single key crypto system, right? So symmetric crypto system is a system where D and E both are same, or D can be, trivially derived from E. Okay, you can easily compute D from E. So all such systems which are based on this particular phenomena where D and E are same, means the key which is used for encryption is same as the key which is used for decryption. Okay, then it is known as symmetric key encryption. If it is not true, if the decryption key is different from encryption key, then we call such system as asymmetric encryption or asymmetric crypto system. Okay, so they are not equal, and you cannot actually compute. If I will give you encryption key, it is computationally infeasible to derive D out of it. Okay, and such systems are known as asymmetric crypto system, public key crypto systems, and things like that. Actually, in this symmetric crypto system, we are using one key, single key, for encryption as well as for decryption. Whereas in asymmetric crypto system, we are using two different keys. One is for encryption and one is for decryption. Okay, so there is a notion of private key and public key, where one particular key is used for encryption, whereas its complementary key is used for decryption, and vice versa. Okay, so let's assume that you are dealing with a simple plain text. Again, I'm taking the same example. Let's say hello, or take it a more simple example. Let's say A, B, C, D, E. This is the plain text which I possess, right? Now I want to encrypt it. Okay, one possible method to encrypt it. So what is this? This is actually M that we are considering. Okay, this is the message that we need to encrypt. Now what is my algorithm? Let's come up with a very simple algorithm. And the algorithm says, the encryption algorithm says that, okay, what you can do is you can add 1 to the ASCII value of this, or maybe you can add any number. Okay, so whatever is the message, you can add some number, say K, okay, to the ASCII value of that particular message or letter. Okay, and whatever is the output will become your ciphertext. Okay, so this is the algorithm. This is the algorithm. E is the algorithm which says you have to add a constant number to the ASCII value of the entire message. Okay, now so this algorithm is known to everyone. The algorithm is out there in public, and this is what open design says, right? So this is known to everyone. Now where the secrecy lies, in this particular example, what should be the value of key?
Ma'am,
This
K
Right, very correct. So what should be the value of k is something which is secret. Okay. So if I would like to send an encrypted message to you and we decided to follow this algorithm, what now we need to do? We need to decide some particular key, that will be used. Okay. So suppose I will say that let's use the key 1 for now. Okay. So what will become the encryption algorithm with key 1? Okay. What will be the output? The output will be B, C, D, E, F. Now this will become our ciphertext. Okay. So can you see the elements of the quintuple elements of the crypto system, right? So we have our message M, we have our ciphertext, we have a set of key, in this case it is 1. Okay, we have one encryption algorithm. Now definitely if you want to read the message, and if you are reading B, C, D, E, F, you maybe cannot derive any meaning out of it, right? It should be something meaningful. What you need is you need the decryption algorithm, how you can reverse this algorithm. Okay, so what will be the decryption algorithm? The decryption algorithm could be just take the ciphertext and subtract it with key. So decryption is the reverse of encryption. Okay? The way in which you encrypt your data in decryption, you have to just reverse all those steps and you will get the plain text. Okay, so this is the decryption algorithm and this is the fifth element of our tuple. Definitely here k you will keep the same because we already agreed, both of the parties are agreed on k equal to 1. So when we decrypt this, we will again get A, B, C, D, E. Okay, so we will decrypt it with 1. Okay, and this is how the crypto system works. Which type of algorithm this is? Symmetric or asymmetric?
Symmetric.
Why symmetric?
Because there is a key, there is a particular unique key that can only decrypt or encrypt the data.
Right, because sender and receiver of the data are sharing one single key. Okay, one single key. When sender and receiver both have different keys, then we consider it as asymmetric key algorithm. Symmetric and asymmetric both are equally powerful, both are equally strong, because in these cases all the security lies based on how you keep these keys secret. Okay, in both of the cases, if you leak your key, then you are gone. The crypto system was broken down, right? You cannot achieve what you want to achieve in both the cases, right? It's not like that in asymmetric key, if public key is known, okay, it doesn't matter, you don't know the private key. No, this is not the case. Okay, if any of the key leaked, your security is hampered actually. Okay, so both the ways are equally strong. And let me tell you one more thing, that when we learn more about these algorithms, you will get to know that in practice symmetric crypto system is generally used more than a symmetric crypto system. Let's talk a little bit about cryptanalysis. Now, we have seen our crypto system and we have seen that, in our crypto system, there is something called encryption algorithm and decryption algorithm. And along with encryption and decryption algorithm, we have to enter some key, right? Which will actually take plain text and then convert it into ciphertext. Now, cryptanalysis is the study of methods for obtaining some meaning of this encrypted information without access of the secret information or without the key. Okay, so let's say Alice is sent some encrypted data to Bob. Now there is someone in between, let's say Eve get the access of the message. Okay, but the problem is the message is in the encrypted form. Okay, this is the message. What Eve can do is Eve can apply cryptanalysis. Cryptanalysis means obtaining, because see, if now Eve read that data there is no meaning out of it, right? So suppose the plain text, sorry, suppose the plain text is hello, right? And the encrypted text is XYZPB. Now with XYZPB, Eve cannot derive anything. So cryptanalysis is actually study of obtaining some meaningful data or meaningful information from the encrypted data without actually accessing the secret information. If Eve knows the key, then so there is no problem, right? They just have to apply the decryption algorithm, because anyways encryption algorithm is known to everyone. You have to apply its corresponding decryption algorithm. The only thing which is secret is the secret key. Okay, if Eve get access of that key, then we are done. But cryptanalysis, what these people actually, cryptanalysts, try to do is they try to obtain some meaningful information from this ciphertext without actually accessing the secret information. Even they try to get the access of that secret information, or they actually try to get the access of the key, that if this is the ciphertext, what could be the possible plain text, what could be the possible key, okay, things like that. And this is known as cryptanalysis. So it typically involves knowing how the system works, okay, how it is encrypted, finding the secret key. So it also referred as code breaking or cracking the code, okay. So the goal of adversary in this is, get to know the plain text corresponding to the ciphertext, or get to know the key, which is used for encryption. Okay, and in cryptanalysis, we generally assume that adversary actually knows the algorithm. The only thing which is hidden is key. Okay, because we are following the open design principle. Okay, so this is our assumption. So now let me tell you what are the possible attacks which are based on this cryptanalysis. So there are three possible attacks that could occur. First attack is called ciphertext only attack. In ciphertext only attack, the adversary has only the access of the ciphertext. Okay, so the case that we have discussed in the previous slide, Eve is having access of this information, nothing else. Okay, only the ciphertext. Goal is to find its corresponding plain text and the possible key. Okay, there are some other attacks which can called as known plain text attack. Now in this case, adversary has the ciphertext and its corresponding plain text. Okay, so both the texts are available to the adversary, and his goal is to find the key. Okay, he knows that this encryption is used. What is the key? This is the goal. Okay, there is another attack which is called chosen plain text attack. Okay, now in chosen plain text attack, you know what happened? Adversary will choose some particular plain text, and then he will give it to the system or the encryption algorithm to encrypt. And by analyzing those special type of uh, uh, conversions, adversary can derive lots and lots of things. Like he can derive which key has been used, etc. Okay, so for example, this adversary can give this text a. Okay, now this is a particularly specially designed chosen plain text which is given to the system, and by observing the output, that how the algorithm actually convert this into the ciphertext, he can actually guess, or he can actually find out the possible key which is there. Okay, now the basis of this attack are in two possible ways. So first is the mathematical attack based on the analysis of underlying mathematics, right? So if somebody will give us a b c d e, and the cipher is its corresponding ciphertext as b c d e f, then by applying maybe some mathematical formula, or by applying some underlying mathematics, we can attack, or we can find out the key or something like that. Okay, and there are many, like this is a very trivial example that I'm giving you, but as we proceed in this particular unit, we will see that there are quite a powerful mathematical techniques that can be applied to break the code. Another type of attack could be statistical attack. Okay, in statistical attack, adversary makes some assumptions about the distribution of letters, pairing of letters, right? So there are some attacks which are based on frequency analysis, right? And it like for example, this English language, right? In English language, there are lots and lots of study which shows that E is a letter which is having high frequency. If you write a message or one page or two page, document, and you count number of frequency of each letter individually, then more. I mean, there are high chances that E is coming a lot more times than other character and things like that, right? So there are lots and lots of frequency analysis on one letter, on pairs of letter, right? So for example, ing. Okay, so generally, I mean, by analyzing that something is ending with ng, there is high probability that I will come before this thing. Okay, so trigrams, diagrams, single letter, and many more, quadgrams, etc. So there are lots and lots of assumptions and statistical analysis which can be done on the distribution of letters, through which the attack can be fired. Okay, so these are called models of the language. So in this, we are examining the ciphertext and correlate the property of the ciphertext by having these assumptions, and somehow we are trying to get the plain text. Okay, so these are the possible attacks. I mean, these are the basis of the attacks that could happen in general, which is used by cryptanalysts. Okay, now one most common attack that could be there is brute force attack. Okay, so the type of cryptanalysis when the attacker has both plain text and the ciphertext of the message, and suppose they try to figure out what is the key that has converted this plain text into the ciphertext. What is a possible way he can do it? So for example, there is one example that we have covered, I think this one. Okay, so where we have used some key to get this, right? So if I tell you that I give you this plain text also and the ciphertext also. Now how can you guess, or how can you apply some method to get this value of this k? Just by seeing that since this is written in English, definitely the value of k is somewhere between, so let's not consider 0 because then we are come up to the same number. It should be somewhere between 1 to 26 or 25, right? Or let's say 0 to 25 in the worst case. Okay, that's it. So this is only 26 values we need to try and we are done. Definitely one combination will give us right answer, right? So in brute force attack, now what I would like to somehow explain here is that by having the knowledge of the language, or by having some observations, you can actually reduce the state space of key. I mean, significantly you can reduce it, right? And this is what happened with brute force attack. So in this, I mean, you have to check all possible keys, but if you can apply some statistical observation, you can actually reduce the number of these possible checkings. And this is where, you have to somehow defend your algorithm from happen. Okay. What we try to do, see, if we talk about brute force attack, brute force, the definition says you can try everything. Okay. Then how can we defend our algorithm? Attacker can try anything and he can get the right answer some or the other time, right? The only thing we can do is somehow we have to make our key space very, very large so that it become computationally infeasible for the attacker to fire brute force attack on our algorithm. Are you getting my point? Okay, this is how we can defend brute force attack. We have to make the key space very large. There should be, many number of keys which could be possible to crack the system, and it should not be computationally feasible for the attacker to test all those keys. Are you with me here? Yes? Yes or no?
Yes, ma'am.
All right. So now it is also very important to realize that now computers are also speed up over time. Okay. What we consider right now very large, it may be possible that after 10 years it will not become that large. Right. So you have to somehow upgrade this definition over time. So very large is somehow very um, subjective thing, because you have to consider a lot many things into consideration. What is the your how is your computational power growing actually? Okay, so the overall goal to defend from brute force attack is we have to make it impractical for the adversary to able to check every single key. Okay, we just need to increase the key state space so that brute force attack is not possible, right?